Hello everyone, let's find out what is the relationship between electric field and electric potential. Recall that the reason that we chose potential to study is because potential is a scalar quantity and electric field is a vector quantity. It is easy to study scalars than vectors, and also it is very easy to deal with scalars and vectors. That is, while adding or doing any operations, scalars are very easy. So we want to understand the charge and its physical parameters in a more simpler way, that is potential. But we know that field is the one which is causing force. So now the point is we need to connect what is the relationship between potential and the field. How are they connected? Because these two are nothing but the same thing studying in different ways. We're trying to find the behavior or how does a charge act in terms of different parameters called as field and potential. We need to connect them. To understand this, to connect them, we'll take a case where we have two surfaces which are equipotential. Example, a surface of this kind and something like this. These two are parallel to each other. Let us call this as surface A and this is surface B. Let the potential at any point on the surface be V. The potential on the surface be V minus dV. So we are assuming that potential is decreasing from surface A to surface B, but both A and B are equipotential surfaces. Let's recall what is the electric field due to a point charge. It is given as K Q by R. So if you have a positive charge somewhere here, then if you look at some distances or if you look at the field direction, the field goes out like this. If we take points 1 and then points 2, it is very obvious that the field at the point 1 would be greater than the field at point 2, and also from this formula the potential at the point 1 would be more than that at point 2. So since we've taken this to be less potential, electric field will go from the surface 1 to surface 2, and since it is normal, the field goes out like this. So the electric field goes out normal to the two surfaces. Let this be 2 points. We'll take a point as say some C and then some point D here. A and B are surfaces, C and D are the points. Now this would be electric field. Now suppose imagine that if you place a positive charge, a charge here, this charge will move with the field like this. Assume that we want to move a charge, small q, from D to C. So you want to move charge from D to C. So this would be our displacement. It's not very big here, but the distance is very, very small. So let the separation between them be some dr. So if you want to move from A to here, from D to R, then the work done to move from D to C is equal to force into displacement. The force here is a force what you're applying. It's the applied force. So here F is the applied force. But the force what you apply here to move from D to C is the force which we need to counter or balance because of the electric field. Otherwise, the charge will move along the electric field. So this force what I apply here is to counter the Coulomb force. Coulomb force will act in this direction. It acts like this. We call it as, say, F Coulomb. So F Coulomb and this force are in opposite directions. Therefore, the work done to move from D to C would be minus of, and Coulomb force is Q into E. That will be Q into E into dr, because the angle between this Coulomb force and this is 180 degrees. If by definition we know that the work done to move unit charge, so if Q is equal to 1 Coulomb, so the work done to move from D to C would be minus of E into dr. This is what is the work done to move from D to C. Let's call this 1. And by definition of potential, we saw that the work done to move from initial to final point by the charge moved is equal to V final minus V initial. Same thing here, the work done to move from D to C, and here Q is 1 Coulomb, that goes away. It is equal to V final, that will be Vc minus Vd, and Vc here is the potential on the surface, which is V, minus Vd would be V minus dV. If we open the brackets, then we get work done to move from D to C is equal to V minus V plus dV. From here V gets cancelled. So finally what we get is work done to move from D to C is equal to just dV, or as 2. Keep in mind that we obtained 1. This is obtained from definition of work done. So this is what is definition of work done, and when we obtain this from definition of electric potential, keep in mind we obtain them in different ways, but both are work done only. So equating them, what we get is we get minus of E into dr is equal to dV. Finally what we get is we get E is equal to minus of dV by dr. A very important expression. In vector form, we can write this vector form as E is equal to minus of dV by dr into some direction that I call as r cap, some direction. This is sufficient to understand initially. It's minus of dV by dr. Now from here, suppose this tells us that if you know what is the potential, you can find electric field. Now vice versa. Suppose if you know what is the electric field, then in that case can we find the potential. For example, recall what is electric field due to an infinitely large wire. Electric field was given as lambda by 2 pi epsilon into 1 by r. In such cases, knowing the electric field, can you find the potential? You can do it. To do that, let's recall what is E. E is equal to minus of dV by dr. If somehow cross multiply, then dV is equal to minus of E into dr. We want only V, so integrate on both sides, and what you get is, it will be like, say, potential at this point is V1, this is V2, it becomes R1 and then R2. So here V2 minus V1 is minus of E into dr. So this is the form of a difference electric potential. So we can do in both the ways. So if you know what is V, you can find what is electric field. If you know what is the field, we can find what is the difference in potential. That's how we do it. Now let's look at some properties of these two parameters. Let's recall what is E. E is minus of dV by dr. So here the minus sign indicates that the direction of electric field is always in the direction of decreasing potential. We saw it in case of point charge also. The point charge somewhere here, then if you look at points like a point 1 and then point 2, the potential as you go would decrease. So potential at the point 1 is more than that at point 2, but the field is going from 1 to 2. So the negative sign indicates that the direction of electric field is always in the direction of decrease of electric potential. Second point is electric field is in the direction of in which the potential decreases steepest. To understand this, see mathematically this form, that is E is equal to minus of dV by dr. This itself is called as a gradient. It's called as potential gradient in this case. Now this itself means that the change occurs along the steepest path. For example, to understand this, think there like a mountain peak here. There are many paths to it. We can have many ways. So there's one side this like this and one like this. So if suppose something is kept from here, think there are different sides to this mountain. Think of 3D view. If something is kept from here, this object, for example, think like a stone. This stone can come to the ground in different paths. It can come like this, like path 1, path 2, or 3 or 4. But this stone would choose the path where the steep or the slope is very, very steep. So if you have steep something of this kind, you have something of this kind, this is very, very steep. It's very almost narrow. It's almost normal to the surface. So this stone would choose this path only. Let's call it path 5. So mathematically itself, this is the meaning of gradient. Mathematically, we can say that change would be along the direction where the slope is steepest. Example, I'll give one more example to it. Think there's like a water coming here. There are many paths to water. Say there's the path for water like this. There's a path like this. There's a path, say, like this. There's a path like this. So we have, say, 1, 2, 3, 4 paths. Suppose water is entering, say, from some opening. Water comes like this. Now this water has to choose 4 paths. Either path 1, 2, or 3, 4. But here the path 2 has the steepest change. It's very steep here. So water would go along this only. So water will go along the path 2. That's what it means mathematically. So whenever we find a gradient, it means the change is along that gradient only. So this point 2 tells us that electric field is in the direction in which the potential decreases steepest. Third point is the magnitude of electric field is given by the change in potential per unit displacement normal to the surface. What it means here is E is equal to minus of dV by dr. If we look only at its magnitude, then in terms of magnitude, E is equal to dV by dr. It says the magnitude of electric field is given by the change in potential per unit displacement normal to the equipotential surface at that point. So this is what is given here. Now think of a case where the field is uniform, that is where we have a uniform field like this, and then if you have two surfaces, a surface like this and surface like this. Suppose if distance between them is d and difference in potential is v between them, in that case we can say E is equal to v by d. Now this form is also very, very useful if you have a case where the electric field is uniform as given in this case. Keep in mind that V is the difference in potential, not on any one surface. It is difference in potential between the two surfaces. So this is the relationship between electric field and electric potential.